Good day everyone, my dear classmates, and to our instructor, Sir Jobert PLD Lab. Hello. Let me introduce to you all. My name is Roylan E. Mispardero, BS1 Science. My lesson is about to discuss two topics. First, inorganic chemistry, which is ionic band and covalent band, and the second one is thermodynamics, which is temperature and heat. So now, let me explain first the ionic band and covalent band. So here's are the objectives. Letter A, contain standards. How atoms combine with other atoms by transferring or by sharing electrons. Letter B, performance standards. Analyze the percentage composition of different brand of two food products and decide on the product appropriate percentage composition. And letter C, learning competencies. Recognize different types of compound, ionic or covalent bond. Here's the objectives. Differentiate between ionic and covalent compound and explain the difference of ionic and covalent compound based on their properties. Content. Ionic bond and covalent bond. So, what is ionic bond and what is covalent bond?
Ionic bonding is a type of chemical bonding that involves the electrostatic attraction between oppositely charged ions or between two atoms with sharply different electronegativities and is the primary interaction occurring in ionic compounds. It is one of the main types of bonding along with covalent bonding and metallic bonding. Ions are atoms or groups of atoms with an electrostatic charge. Atoms that gain electrons make negatively charged ions called anions. Atoms that lose electrons make positively charged ions called cations. This transfer of electrons is known as electrovalence, in contrast to covalence in the simplest case. The cation is a metal atom and the anion is a non-metal atom, but these ions can be of a more complex nature. Example, molecular ions like NH+/4 or SO2-4. In simpler words, an ionic bond results from the transfer of electrons from a metal to a non-metal in order to obtain a full valence shell for both atoms. Sodium and fluorine. Atoms undergoing a redox reaction to form sodium ions and fluoride ions. Sodium loses its outer electron to give it a stable electron configuration, and this electron enters the fluorine atom and exothermically. The oppositely charged ions, typically a great many of them, are then attracted to each other to form solid sodium chloride. It is important to recognize that clean ionic bonding, in which one atom or molecule completely transfers an electron to another, cannot exist. All ionic compounds have some degree of covalent bonding or electron sharing. Thus, the term ionic bonding is given when the ionic character is greater than the covalent character. That is a bond in which a large electronegativity difference exists between the two atoms, causing the bonding to be more polar ionic than in covalent bonding, where electrons are shared more equally. Bonds with partially ionic and partially covalent character are called polar covalent bonds. Ionic compounds conduct electricity when molten or in solution, typically not when solid. Ionic compounds generally have a high melting point depending on the charge of the ions. They consist of the higher charger, the stronger the cohesive forces, and the higher the melting point. They also tend to be soluble in water. The stronger the cohesive forces. Covalent bond. A covalent bond is a chemical bond that involves the sharing of electron pairs between atoms. These electron pairs are known as shared pairs or bonding pairs, and the stable balance of attractive and repulsive forces between atoms when they share electrons is known as covalent bonding. For many molecules, the sharing of electrons allows each atom to attain the equivalent of a whole outer shell, corresponding to a stable electronic configuration. In organic chemistry, covalent bonds are much more common than ionic bonds. A covalent bond forming right where two hydrogen atoms share the two electrons. Covalent bonding also includes many kinds of interactions, including a bonding, eye bonding, metal-to-metal bonding, acoustic interactions, bent bonds, 3-center 2-electron bonds, and the 3-center 4-electron bonds. The term covalent bond dates from 1939. The prefix co means jointly associated in action, partnered to a lesser degree, etc. Thus, a covalent bond in essence means that the atoms share valence, such as is discussed in valence band theory. In the molecule, the hydrogen atoms share the two electrons via covalent bonding. Covalency is greater between atoms of similar electronegativities. Thus, covalent bonding does not necessarily require that the two atoms be of the same elements, only that they be of comparable electronegativity. Covalent bonding that entails the sharing of electrons over more than two atoms is said to be dicolysis.
Chemical bonding. Almost everything we see or touch in our daily life is the result of a chemical bond. The air we breathe, the food we eat, the clothes we wear, and so on, are all made up of one or more chemical bonds. The world is generally not composed of isolated atoms. Rather, it is composed of molecules formed as a result of chemical bonds. The strong force that holds together the constituent particles, atoms, ions, or molecules in a chemical species is known as chemical bond. The chemical bonds are broadly classified as ionic bond, and covalent bond. Let us discuss these chemical bonds in detail in this module. The bonding which results due to the complete transfer of valence electrons between atoms is called ionic bonding. It is a type of chemical bond that generates two oppositely charged ions. Ionic bonding is observed because metals have few electrons in its outermost orbital. By losing those electrons, these metals can achieve noble gas configuration and satisfy the octet rule. Similarly, non-metals that have close to 8 electrons in its valence shell tend to readily accept electrons to achieve its noble gas configuration. In ionic bonding, more than one electron can be donated or received to satisfy the octet rule. Sodium metal has electronic configuration as 2, 8 and 1. It has one electron more than a stable noble gas structure. If it gives away that electron, it would become more stable. On the other side, chlorine has electronic configuration as 2, 8 and 7. It has one electron short of a stable noble gas structure. If it could gain an electron, it too would become more stable. Thus, the sodium atom donates its valence electron to achieve stable octet configuration. This creates a positively charged cation due to the loss of electron. The chlorine atom receives one electron to achieve its stable octet configuration. This creates a negatively charged anion due to the addition of one electron. The sodium ions and chloride ions are held together by their strong electronic attractions between the positive and negative charges. Covalent bonding. A covalent chemical bond results from the sharing of electrons between two atoms with similar electronegativities. The electronic configuration of chlorine atom is one electron short of the argon configuration. The formation of the chlorine molecule can be understood in terms of the sharing of a pair of electrons between the two chlorine atoms, each chlorine atom contributing one electron to the shared pair. In the process, both chlorine atoms attain the outer shell octet of the nearest noble gas, that is argon. The dots represent electrons. Such structures are referred to as Lewis dot structures. Thus, the chlorine atoms are joined by a single covalent bond. A single covalent bond is formed when one pair of electrons are shared between two atoms. It is depicted by a single line between the two atoms. A double bond is formed when two atoms share two pairs of electrons with each other. It is depicted by two horizontal lines between two atoms in a molecule. This type of bond is much stronger than a single bond, but less stable. This is due to its greater amount of reactivity compared to a single bond. For example, in the carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. When three pairs of electrons are shared between two atoms in a molecule, a triple bond is formed. It is the least stable out of the three general types of covalent bonds. The two carbon atoms in the ethyne molecule are joined by a triple bond.
Procedures. Reviewing previous lesson or presenting new lesson. Review. Number 1. Which element high or low electronegativity, ionization energy, and valence electron, a metal or non-metal, and why? And number 2. What economic reasons why we need learn properties of metal and non-metal?
Number 1. The electrons in a band are placed further away from the nucleus and are held less tightly. Atoms with high ionization energies have high electronegativities because the nucleus has a strong attraction for electrons. Metal atoms tend to have low ionization energies relative to non-metal atoms. Metal atoms lose electrons to non-metal atoms because metals typically have relatively low ionization energies. Metals at the bottom of a group lose electrons more easily than those at the top. Non-metals have much higher electronegativities than metals, but the non-metals, fluorine is the most electronegative, followed by the oxygen, nitrogen, and chlorine. The larger the difference in electronegativity between two atoms, the more polar the bond between them. And then number 2. The metalloids are semi-metals have properties that are somewhat of a cross between metals and non-metals. Metalloids tend to be economically important because of their unique conductivity properties. They only partially conduct electricity, which make them valuable in the semiconductor, computer chip industry.
In this lesson, we're going to talk about ionic bonds, covalent bonds, particularly polar covalent bonds and non-polar covalent bonds. So let's say if we have this bond, the bond between two hydrogen atoms. would you describe this bond as ionic, polar covalent, or non-polar covalent? Anytime you have a bond between two atoms of the same element, it's always going to be a non-polar covalent bond. Now, the reason why it's a covalent bond is because the electrons in this bond are shared equally, due to the fact that we have the same the same type of atom, and so therefore they have the same electronegativity, and so they pull on those electrons with an equal force. So because the electrons are shared equally in this molecule, it's going to be a non-polar covalent bond. Now here's another example for you. What about the carbon-oxygen bond? Would you describe it as ionic or covalent? Now, anytime you have a bond between two nonmetals, typically it's usually a covalent bond. So we need to determine if it's a polar covalent bond or a non-polar covalent bond. And we need to look at the electronegativity values of these two elements. So here are some numbers that you want to be familiar with. Hydrogen has an electronegativity value of 2.1. Boron is about, let me list out the elements: boron, carbon, nitrogen, oxygen, and fluorine. So boron's about 2.0, carbon is 2.5, N is 3.0, O is 3.5, F is 4.0. And these values are based on the textbook I'm using. Some textbooks might have slightly different values, but you want to use the values based on the textbook you're using. So carbon has an electronegativity value of 2.5, and oxygen has a value of 3.5. If the electronegativity difference is 0.5 or more, then the bond is said to be polar. If the electronegativity difference is 0.4 or less, then the bond is said to be nonpolar. So 3.5 minus 2.5, that's 1. So therefore we can say that the carbon-oxygen bond is a polar covalent bond. The electrons are being shared, but not equally. Now, because oxygen is more electronegative than carbon, it's going to have a partial negative charge. And carbon, because it's less electronegative than oxygen, it has a partial positive charge. So how can we indicate bond polarity? How can we show the dipole moment in this bond? You need to draw an arrow pointing towards the more electronegative element. And so whenever you see a dipole moment like this, it tells you that this bond is a polar bond. Now, what about the bond between sodium and chlorine? Would you describe it as ionic, polar covalent, or non-polar covalent? Sodium is a metal. Chlorine is a non-metal. And typically, when you have a metal mixed with a non-metal, for the most part, it's safe to say that it's going to be an ionic bond. Sodium chloride is made up of ions. In this substance, sodium has a positive charge, and chlorine has a negative charge. Positively charged ions are known as cations, and negatively charged ions are known as anions. And so that's why we have an ionic bond. We know that opposite charges attract, and so there is an electrostatic force of attraction that keeps these ions held together, and that makes the ionic bond. So typically, whenever you have a metal mixed with a non-metal, ionic interactions are usually created. Now, it's important to understand the difference between an ionic bond and a covalent bond. In a covalent bond, the electrons are shared. In an ionic bond, the electrons are transferred. So, in a polar covalent bond, they're shared unequally, but in a non-polar covalent bond, the electrons are shared equally. Sodium has 11 electrons, but it has 1 valence electron. Chlorine has 7 valence electrons. So when you put together, let me draw this differently, an atom of chlorine and sodium, Sodium, it's going to give away its one valence electron to chlorine, and when it loses that electron, it acquires a positive charge. When chlorine accepts it, it's going to have 8 valence electrons, and so it's going to be negatively charged since it gained an extra electron. So after this transfer of electrons, there's going to be an electrostatic force of attraction that holds these ions together, and so that makes up the ionic bond. Now let's talk about the hydrogen atoms that make up the H2 bond. Let's say if we have 2 individual atomic hydrogen particles, both of which contain 1 valence electron. When these 2 get together, they will each give up their valence electron to form a covalent bond. And so the 2 electrons represented by that bond are shared equally among those hydrogen atoms, and that's why it's a non-polar covalent bond. The electrons are shared. In an ionic bond, you had a transfer of electrons. Sodium gave up an electron, chlorine accepted it. But here, both hydrogen atoms contributed an electron to create this covalent bond. And so that's why it's not ionic, but it's covalent. You have a sharing of electrons as opposed to a transfer of electrons. Now let's go through some more examples. So what about the carbon-hydrogen bond? Would you describe it as ionic, polar covalent, or non-polar covalent? Now carbon has an electronegativity value of 2.5, and for hydrogen it's 2.1. So the electronegativity difference is 0.4, which means that this bond is nonpolar. Whenever you see a molecule that contains only carbon and hydrogen bonds, it's a nonpolar molecule. For example, methane is nonpolar, it doesn't mix with water. Or hexane, C6H12, that's a nonpolar molecule. They don't dissolve in polar substances like water or like alcohol. Now what about the carbon-carbon bond? Is it ionic or is it covalent? Now, both substances have the same electronegativity value, so the En difference is 0, which means that it's nonpolar. So anytime you have 2 of the same type of atoms that make up a bond, it's always going to be a nonpolar bond. The electrons will be shared equally. Now what about the OH bond? What can we say about it? Is it an ionic bond, a polar covalent bond, or a non-polar covalent bond? Well, let's start with the electronegativity values. Oxygen has an electronegativity of 3.5, and for hydrogen it's 2.1. So the electronegativity difference is 1.4. So this bond is highly polar. Now, it's a special type of polar bond. Anytime you see hydrogen directly attached with nitrogen, oxygen, or fluorine, it's a special type of bond. Do you remember what it is? It's known as hydrogen bonding. These are very powerful intermolecular forces. Because of hydrogen bonding, water has a very high boiling point for being a molecule. Most molecules have low boiling points, but those with hydrogen bonds, they have relatively high boiling points. So we have a polar covalent bond with a special case of hydrogen bonding. Now let's indicate the bond polarity. Because oxygen is more electronegative, it's going to have the partial negative charge, and hydrogen is going to have the partial positive charge. So to indicate the dipole moment, we're going to draw the arrow towards the more electronegative element. Now let's consider one more example. What about the bond between lithium and fluorine? Would you say it's an ionic bond, a covalent bond? And if it's covalent, is it polar covalent or non-polar covalent? Lithium is a metal, fluorine is a non-metal. So automatically, just by identifying the type of element that we're dealing with, we know it's going to be an ionic bond. The electronegativity difference between lithium and fluorine is huge. But for the most part, if you have a metal and a non-metal, it's safe to say that you have an ionic interaction. Lithium is a positively charged cation, and fluoride is a negatively charged anion.
Calculate the difference of electronegativity value of given compound. Ionic compound difference of 2.0 pound, electronegativity 1.9 plus 0.4 is polar covalent, less than 0.4 is non-polar covalent. So here's our analysis. Question number 1. What type of compound?
We will need salt, sugar, 2 glasses filled with water. First, we will take equal quantities of water in 2 glasses. Now put a spoonful of common salt in 1 glass and a spoonful of sugar in other. Do not stir the water. Observe closely. Which one passes on to the solution first? Which has a better rate of dissolution? We find that salt dissolved before sugar and hence its rate of dissolution is faster than that of sugar. The rate of dissolution is the rate at which a solute dissolves in a solution. This rate of dissolution is different for different solutes. It depends on the chemical makeup of the solutes. Beside these, we will need beakers, 2 carbon rods, bulb, battery eliminator, wires and filter paper. First, connect the carbon rods to the 2 terminals of a battery eliminator through a bulb and switch it on. Now dip the 2 carbon rods in a beaker containing hydrochloric acid and observe. The bulb glows, showing that the circuit is complete. This means that the hydrochloric acid conducts electricity. Remove the carbon rods, dry them with the filter paper, and then put them in sodium hydroxide solution. The bulb glows once again. So even sodium hydroxide solution can conduct electricity. So both acidic solution and basic solution conduct electricity, or in simple language, allow electricity to pass through. This is because when acids are dissolved in water, they break down to hydrogen ions and a negative ion, while bases give hydroxide ion and a respective positive ion. The movement of these ions conducts electricity.
The one on the left is somewhat cold to the touch, while the one on the right is slightly warmer. How much longer do you think it would take an ice cube to melt on the cold block on the left compared to the warmer one on the right? Well, in fact, this is a misleading question. The cold block and the warm block are both at the same room temperature, and as you can see, the ice cube on the left on the cold block actually melts very rapidly, probably melting completely in less than about 2 minutes. In the same period of time, the ice cube on the right, the warmer block, has not melted to the amount that you can even be noticed. There are 2 discrepant events here. 1. Things at the same temperature can feel as though they are at different temperatures. 2. The ice pieces on the 2 blocks melt at extremely different rates in a way that is completely unexpected. The cold block on the left is made of aluminum, which has the highest heat conductivity of common materials. It feels cold because the heat of your hand, which is much warmer than room temperature, is rapidly conducted into the aluminum. This cools your hand much more than you would expect upon touching a room temperature object. Your brain tells you, hey, the block is cold. The warm block is made of a rigid foam plastic. The plastic is a poor conductor of heat. The air and gas bubbles inside this makes it especially so. The heat is conducted more slowly from your hand than experienced. You would lead you to expect your brain tells you the block is warmer than room temperature. Since the cold block on the left is made of aluminum, Thus, the heat of the block flows into the ice cube. The warm block is of the rigid plastic, which is not a good insulator, thus a poor conductor of heat.
Number 2. Example. Why salt and benzene can conduct electricity in solution?
A unique compound like salt and benzene give off positive cation and negative anions. Ions in solution, that is why they can conduct electricity. Salt and benzene release sodium action. Salt also releases chloridion in aqueous solution, while benzene releases glutamate anion.
Number 3. Make a general statements about the properties a unique and covalent compound. Assessment for application. Calculate the percent of composition of 40.0 gram nitrogen and 250 gram NaO3. And now, assignment. List down common diseases of the heart and lung. What are common symptoms of these? And that would be all about inorganic chemistry, a unique bond, and covalent bond. This is Royland Davis Martin of Basic 1 Science. Thank you for watching. God bless us all. Good day everyone, my dear classmates, and to our instructor Sir Jobert L. Dilag. Good day. So, may I discuss to you my lesson is about in thermodynamics, which is temperature and heat. So now, first are the objectives. Letter A, the content standards. In thermodynamics, heat and temperature are closely related concepts with precise definitions. Heat, U star text, and E in text is the thermal energy transferred from a hotter system to a cooler system that are in contact. Temperature is a measure of the average kinetic energy of the atoms or molecules in the system. Letter B, performance standards. The words hot and cold are commonly used to describe the temperature of a material, although the terms hot and cold are not very precise. These still are useful. Everyone understands that hot indicates high temperature and that cold indicates low temperature. Letter C, learning. The atoms in an object are in constant motion. Competencies objectives. The thermal energy of a substance is the sum of the kinetic and potential energy of its molecules. The number 1. The kinetic energy increases as the molecules move faster. And the number 2. The potential energy increases as the molecules move farther apart. So now, let us proceed to our content. The contents are temperature and heat. So what is the temperature and what is the heat? So let's define what is the temperature and what is the heat. So here's are the definition of temperature. Temperature, the measurement of temperature is part of everyday life. We measure the temperature of the air outdoors to decide how to dress when going outside. A thermostat measures the air temperature indoors to control heating and cooling systems to keep our homes and offices comfortable. Regulation of oven temperature is important in baking. When we feel ill, we measure our body temperature to see if we have a fever, despite how matter of fact it may seem. Temperature is a subtitle concept. Although our subjective sensation of hot and cold are related to temperature, they can easily mislead as the next physics of home demonstrates. The definition of temperature is based on the concept of a thermal equilibrium. Suppose two objects of systems are allowed to exchange energy. The net of flow of energy is always from the objects at the higher temperature, the object at the lower temperature. As energy flows, the temperature of the two objects approach each other. When the temperatures are the same, there is no longer any net flow of energy. The objects are now said to be in a thermal equilibrium. Thus, temperature is a quantity that determines when objects are in a thermal equilibrium. The objects do not necessarily have the same temps due to a temperature difference between them is called heat. We discussed heat in detail. If heat can flow between two objects of systems, the objects systems are said to be in a thermal contact. To measure the temperature of an object, we put a thermometer in thermal contact with the object. Temperature measurement relies on the zeroth law of thermodynamics. So that are the temperature of the definition. So now let us proceed to a heat definition. So may I read this definition about the heat? Definition of heat. Heat is an energy transit between two objects or systems due to a temperature differences between them. Many 18th century scientists thought that heat was a fluid, which they called caloric. The flow of heat into an object was thought to cause the object to expand in volume in order to accommodate the additional fluid. Why no mass increase occurred was a mystery. Now we know that heat is not a substance, but is a flow of energy. One experiment that led to this conclusion was carried out by Count Rumford and Benjamin Thompson said in the year of 1753 to 1814. While supervising the boring of cannon barrels, he noted that the drill during the boring became quite hot. At the same time, it was thought that the grinding up in the cannon metal into a little pieces caused caloric to be released because the tiny bits of metal could not hold as much caloric as the large piece from which they came. But Rumford noticed that the drill got hot even when it became so dull, the metal was no longer being bored out of the cannon, and that he could create
a limitless amount of what we now call eternal energy, he decided that heat must be a form of microscopic motion instead of a material substances. It was not until later experiments were done by James Prescott Joule in 1818 to 1889 that Rumford's ideas were finally accepted. In his most famous experiment, Joule showed that a temperature increase can be caused by mechanical means. In a series of such experiments, Joule that determined the mechanical equivalent of heat or the amount of mechanical work required to produce the same effect on a system as a given amount of heat. In those days, heat was measured in calories, where 1 calorie was defined as the heat required to change temperature of 1 gram of water by 1 degree Celsius. Specifically, from 14.5 to 15.5 degrees Celsius, Joule experimental results were within 1% and the currently accepted value, which is, here's now the equation. 1 calorie is equals to 4.186 by Jones is now the 14-1 is now the definition of the calorie. The calorie with an uppercase letter C used the Titans nutritionist is actually a kilocalorie. So 1 calorie is equals 1 calorie is equals to 10 to the power of 3 calorie. Although the calorie is still used, the SI unit of eternal energy and for heat is the same as that used for all forms of energy and all forms of energy transfer. The Joule. So that means, and that could be all about heat and temperature. It's about to explain to you. Learning resources is the references, integrated physics and chemistry books, Glencoe, Science. And in number 4, Google Research Mobile Applications. And in the 5, Learners Materials, page 158 to 163. Then now, let us proceed to number 4, which means procedures. Procedures: reviewing previous lesson or presenting the new lesson. So, start the class with a prayer using multimedia, then roll call, lead group leader report attendance, and number 8 is elicit and review. So, let's discuss about the review. Let's review letter A. Explain the differences between heat and temperature. So now, what is the differences of heat and temperature? Heat describes the transfer of thermal energy between molecules within a system and is measured in joules. Temperature, heat, measures how energy moves or flows. Temperature describes the average kinetic energy of molecules within a material of system and is measured in Celsius, degrees Celsius. Kelvin key is a Fahrenheit, degrees Celsius, or Rankine is R. So let's proceed to what is thermal energy and what causes it to change. Thermal energy, also called heat energy, is produced when a rise in temperature causes atoms and molecules to move faster and collide with each other. The energy that comes from temperature of heat substance is also called thermal energy. In letter C, how is heat transferred between two objects? The heat capacity, suppose we have a system in which no mechanical work is done, but we allow heat to flow into the system by placing in a thermal contact with another system at higher temperature. Then, what is specific heat? Specific heat, the heat capacity of the water in a drinking glass, is much smaller than the heat capacity of the water in Lake Superior. Since the heat capacity of system is proportional to the mass of the system, the specific heat capacity is a symbol of letter C of a substance defined as the heat capacity per unit and mass. Specific heat capacity is often abbreviated the specific heat. The SI units of the specific heat are J/K.K. In SI units, the specific heat is the number of joules of heat required to produce a 1 K temperature change in a 1 kilogram of the substance. Again, since the only temperature changes are involved, we can equivalently write G/kilogram and degree Celsius. List of specific heats for some common substances at what atm and 20 degrees Celsius, unless otherwise specified, with the range of temperature in our examples. Problems assume these specific heat values to be valid. Note that water has a relatively large specific heat compared with the most other substances. The relatively large specific heat of approach moderating the temperature along the coast. So that are about the temperature and heat in about to review. So let us proceed in the letter F, establishing a purpose for the lesson. Engage motivation. Heat flows from the warmer ingredients inside the container to the ice and salt mixture. The specific heat of water is high because water molecules form strong bonds with each other. When heat is added, some of the added heat has to break some of these bonds before molecules can start moving faster. In metals, electrons can move freely. When heat is added, no strong bonds have to be broken before the electrons can start moving faster. These are the specific heat of some common materials. Substance: water, wood, carbon or graphite, glass, and iron. The specific heat, joules, degrees Celsius, Kelvin, and grams. In water is about 4,184. In wood is about 1,760. In a carbon or graphite is about 710. Glass is about 664. Iron is about 450 specific heat.
There are lots of different scales for measuring temperature. Fahrenheit and Celsius are the most commonly used in everyday life, but Fahrenheit is almost never used in science. The Celsius scale is based on the freezing point and boiling point of water. But even the Celsius scale isn't the best, because absolute zero on the Celsius scale is negative 273.15 degrees. The Kelvin scale is based on absolute zero and starts at 0 Kelvin with no negative numbers. 1 degree Celsius is equivalent to 1 degree Kelvin. Absolute zero is where the kinetic energy of atoms is zero, well, theoretically. It's easy to switch between Celsius and Kelvin. Just subtract 273.15 from Kelvin to get Celsius, or add 273.15 to Celsius to get Kelvin. For example, 20 degrees Celsius is 293.15 Kelvin. And make sure you don't say degrees Kelvin. It doesn't actually use degrees, it's just Kelvin. When particles of a gas are heated, the particles will speed up. This means that the kinetic energy of the particles has increased and therefore the temperature of the gas has increased. But the reality is that not every particle is moving at the same speed. We'll start by viewing a scale that measures the relative number of particles at different speeds. Particles are always moving unless they're at absolute zero. These few particles with a slower speed have less kinetic energy, and these particles with faster speeds have higher kinetic energy. But we can't easily take a snapshot of just one or a few particles. When we measure the temperature, we're looking at the average kinetic energy of many particles. This bell curve may represent a fairly warm temperature, and this curve a relatively lower temperature. There are lots of particles that have the same kinetic energy at both of these temperatures, but again, temperature is the average kinetic energy of particles. If the temperature drops to absolute zero, the kinetic energy of the particles comes to a halt. This is where the Kelvin scale starts, which means that there are no negative numbers in Kelvin. It begins at 0, making it better than Celsius, but there's another reason that Kelvin is better than Celsius. It's better mathematically. If the temperature rises from 10 to 20 degrees Celsius, it appears to have doubled. But if you convert those numbers to Kelvin by adding 273, you'll see that the numbers haven't doubled at all. Kelvin is accurate when it comes to proportions, so use Kelvin in all of your chemistry.
This water boiling, the heat of the fire, and cooking on the skillet are all examples of heat transfer. In simple terms, heat is the transfer of energy from objects of different temperatures. As objects warm up or cool down, their kinetic energy changes. Kinetic energy is the energy of motion. Temperature is a measure of the average kinetic energy of the particles in an object. As temperature increases, the energy of motion increases. As the water warms up and the temperature increases, you can see an increase in the movement. Heat can be transferred in at least 3 ways: conduction, convection, and radiation. Conduction is a process in which the transfer of heat takes place between objects by direct contact. It is most often associated with solids. The key to conduction is direct contact. The heat of the pan is transferred to the mini pizzas. The energy of the frying pan is transferred to the eggs. Notice that they are in direct contact. Convection is heat transferred by the movement of a fluid such as air or water. When the heated fluid is caused to move away from the source of heat, carrying the energy with it. It occurs due to density. Lava lamps are examples of convection. As the liquid is heated, it rises and falls as it heats and cools. As the paper burns, the air is heated up and begins to rise. The burning paper is swept up in the convection current, cools, and falls back down. These beans are another example of convection. As the beans warm up, they rise and then cool and fall back down, and repeat this over and over again. Radiation heat is transmitted without any physical contact between objects. Watch how the temperature of the lamp is transferred to the thermometer without touching it. These alligators and lizards use radiation from the sun to warm their bodies. If you'd like to know more about heat transfer and conduction,
In letter G, discussing new concepts and practicing new skills. Number 10, explore or activity. Interpreting data equal amounts of iron, water, and glass with the same initial temperature were placed in an oven and heat briefly. Use the data in table. Number 1, to match its final temperature with the appropriate material, 515 Celsius, 25 degrees Celsius, and 66 degrees Celsius. Solving one-step equation, calculate the change in thermal energy of 30 degrees Celsius. In letter H, discussing new concepts and practicing new skills. The class will be divided in 4 groups. Each group will perform 15 minutes task. Answer the question in given paper. Each group with 2 representatives each group to discuss the output. The output of each group will be based on the rubrics. So that's all about the discussing about the concepts. Classmates, Sir Jobert L. Dilag, Science Physics and Thermodynamics. That could be all about temperature and heat. This is Royland E. Mismartiro, Basic Science 1. Thank you for watching and God bless us all. Bye bye.